Well, thank you all for coming to my talk, and I would like to thank the organizers for inviting me and to this great conference. So I'm from Rio. This is the entrance of the Guanabara Bay. I hope you have the chance to visit. So this is the outline. I will, after a very brief introduction, I will present some theoretical and experimental results on the screening of the Casimir interaction in electrolytes. And these experimental results are based on optical tweezers. So for this very brief introduction, so if I have a polar liquid, I have ions in solution. The ions can move around, and if I have a particle which is always charged in this environment, these ions are going to move in such a way as to form a diffuse layer around this charged particle. So if I have another particle very far away, this other particle is going to feel just the total charge. So this is the screening effect. So there will be a suppression of the electrostatic interaction because this diffuse layer tries to neutralize the charge of the particle. Right? So this electrostatic interaction is typically exponentially suppressed over this characteristic length scale that we call the bi-screening length, lambda d. So if I think of the van der Waals interaction as arising from, say, dipolar fluctuations, we might wonder if the van der Waals interaction would also be screened like the electrostatic interaction is. And however, there is one important point to think about, which is the fact that the characteristic response of the ions is very slow compared to the Matsubara, to the positive Matsubara frequencies. And this is determined by the plasma frequency of the ions, which is very, very small compared to kBT over h bar. So only the zero frequency is going to be changed by the presence of the ions. So this is something that nobody debates. It's really like this. It's easy to see. So the question that is left is, what about the zero frequency contribution? That is this totally thermal contribution, right? Proportional to kBT that comes from the zero Matsubara frequency. So is it screened? Yes, for sure, but is this screening partial or total? This is the answer. This is the question I would like to address, and I will provide some theoretical and experimental results to this question. And this question is very important because if I have dielectric materials in a say water solution, which is the most important example, of course, also because of the possible biological applications. So in this case, this zero frequency contribution, that purely thermal contribution, is dominant at very short distances already, 100 nanometers. It's very different from the case of metals, right? For metals interacting across a vacuum gap, the thermal contribution, the zero frequency contribution, is dominant only at distances larger than, say, 7 microns or so. This was mentioned by Umar and by Galina earlier. So that means that what happens to this zero frequency contribution is really essential here, right? Because if we conclude that this zero frequency contribution is suppressed, then there will be nothing left in this distance range. On the other hand, if there is some contribution from the zero frequency contribution which is not suppressed, then there will be some signal, right? There will be some interaction left in this distance range. So some theoretical results now. I mean, this is how we approach this theoretically, taking this bulk approximation. So the fact that the ions are movable, right, means that the response is non-local. There has been a lot of discussion earlier, and also 2 days ago by Carsten, right, in the context of electrons, right, in metals or in graphene. I have this non-locality in this context, but here I want to discuss the context of, instead of electrons, I have ions, right, in solution, and there are some differences that I'm going to emphasize during the talk. So this is the, when I have translational environments, because I am in the bulk approximation, this is described by this convolution. And then in Fourier domain, I have this K dependence that Umar was talking about, and Galina also, right, of the conductivity. So to be a bit more specific, and here I'm following this, the way, this formulation by Davis and Ningham, this K-dependent conductivity, this spatially dispersive conductivity leads to a K-dependent dielectric tensor, but the transverse component of the tensor is local, right? There is no K-dependence here. This is just the Drude-like term, and here is the plasma frequency of the ions, which, as I told you, is very, very small. And here is the dielectric constant of pure water, right? It comes from the polarization of the water molecules. This is the one that we can check in tables. What about the non-locality then, the spatial dispersion? It appears only in the longitudinal component of the tensor. And it's this term here, right? The K appears only here, and it comes with this characteristic length scale of screening that I was mentioning before, which is the Debye screening length. So with that, we can now consider the standard configuration with, let's say, to begin with this parallel planar interfaces between a local dielectric and my water solution, which is non-local, right? There are ions here. And then because of this non-locality of this K dependence, I can have longitudinal modes, right? The non-locality allows for longitudinal modes. So my reflection matrix at this interface now is a 3x3 matrix, right? Because in addition to the two transverse polarization components, I also have the longitudinal one. And then this longitudinal component, this L here, couples with transverse magnetic, the P polarization, right? As I reflect at the interface. And then I can use this scattering formula to find the free energy, right? In terms of this round trip matrix, the matrix that describes how the fluctuations propagate back and forth, right? With two reflections and one propagation on each side. So for the problem that we are, for real problems, right? This plasma frequency associated to the ions is very, very small, as I said before, much smaller than kBT over h bar. Then from this general formalism, we can show, right, by looking at the extractions, that the effect of the ions is completely negligible for all positive Matsubara frequencies because of this difference in frequency scale. So only the zero frequency, the thermal contribution, is modified. And in this case, when I take the zero frequency limit, I can simplify this matrix. The non-diagonal terms, they vanish. And I have a simpler form for this reflection amplitude for longitudinal waves, which I show here. It depends on the dielectric constant of the local dielectric, and on the dielectric constant of water, and on the Debye screening length. So it depends also on the concentration of ions. That comes from here, the Debye screening length. So with that, and then from this equation here, this matrix simplifies, and I have two contributions at zero frequency. One is this here that comes from the longitudinal modes, right, which is written in terms of this reflection coefficient. And the other, it's familiar, right? Umar has just written this before in the previous, our previous talk. This is the contribution of transverse magnetic modes, which is also there, right? And turns out to be the same as if I had metals here, right, and vacuum or any other dielectric in between, right? Because I mean the reflection coefficient it's the same if I propagate from this side or from this side. So if I replace one by the other, I have the same final result for this geometry, right? So this is the same result as I have for through the vacuum, through the calculation. Here I have local dielectric, an electrolyte solution, and a local dielectric. So this contribution, back to this contribution coming from the longitudinal modes, this coincides with many different theoretical calculations made from a long time, right, by different people. Only that I think they have never written this in terms of a reflection coefficient, right? I mean, there was in these papers, there is a coefficient here. And here we see that this coefficient is really the reflection coefficient of longitudinal modes at the limit of zero frequency. And this contribution, we can see that it's really suppressed, right? If I take L much larger than lambda d, okay, because this is going to be 0, and then I have a log of 1. So this is really screened like the electrostatic interaction. So there is this screened contribution from the longitudinal modes, but we find another contribution as well from the transverse magnetic polarization, which is not screened, which is this thing here, right? Is this really there or not, right? We are going to do an experiment to try to see if it's really there or not, or maybe this is a problem with this model that we have used. So before talking about the experiment, we have to change the geometry, right? Because no experiment will be made with this parallel planar interfaces, so we need to discuss spherical particles, right? And here, for simplicity, I'm going to assume that the distance between the spheres is much larger than the screening length. So the longitudinal contribution has gone, right? It was completely suppressed, so I will have only the transverse one, only the transverse contribution. The more general case is discussed in Larissa Inácio's poster, right, which is still there, but not for very long, as Ricardo said. So we focus on the zero frequency contribution, right? Because for the positive frequencies, the ions don't matter. So here is the plot of the free energy contribution to the zero, the purely thermal contribution, right? The zero frequency contribution divided by KBT. And this is plotted as a function of this parameter, the distance divided by the effective radius. This effective radius is very useful to represent the so-called proximity force result, which is this region here, very short distances. And here I have different curves corresponding to different values of this parameter here, which is related to how this sphere sizes compare, right? And this can, the largest value of this is 1/4, right? When the spheres have equal radii, which is the green curve. And this can goes to 0 when I consider the case of a sphere and a plane, right? So here I can cover all these cases, right? And for short distances, it doesn't depend on this aspect ratio. But for long distances, of course, it should depend, right? Because if I have two small spheres, it's in the dipolar approximation, it goes as r to the power 6 divided by L to the power 6, right? It's the product of polarizabilities. On the other hand, if I have a plane and a sphere, which is this red one here, I have a different power law, right? It's r over L to the power 3. So this becomes very different even in this log scale, right? As I increase the distance. But there is a very nice way of representing this, capturing this U dependence, right? Which is by introducing this variable Y, right? And I think Fernando has nice papers on this, So this is a conformally invariant parameter. If I plot, instead of plotting as a function of this x, right? If I plot as a function of this parameter here, that you see it contains the u in its definition. So most of the dependence on u is already captured by this definition here, and in particular, the long distance limit, they almost coincide. So most of the dependence on u comes from this conformally invariant parameter y. So this is similar but not identical to the function, the universal function that we find for Drude vacuum Drude, right? For the zero frequency contribution, or for the long distance limit, or in other words, for the high temperature limit, right? So it's another way of mentioning this. But the function has shared these two functions, the one we have discussing here and the one for the Drude vacuum Drude. They share some common features, but they are not the same. They are numerically very different. So although the PFA limit, of course, is the same for both, right? Because then we make the connection with the parallel planar geometry, and then in this case, these two functions are the same. So this is universal. Just before concluding this part, it doesn't depend on the dielectric constants, right? Because this transverse permittivity, regardless of this value, when I take omega to 0, that goes to infinity, right? So there is no dependence on the dielectric properties of the materials. It's just the ionic response that matters in this, for this zero frequency contribution. Okay, so now let's talk a little bit about our experiment. So I will just have a very, very short reminder or introduction to optical tweezers. So optical tweezers are these optical traps where I use a single laser beam that crosses a high numerical aperture objective, and the particle is going to be trapped near the focus of this beam, right? So that works provided that this is highly focused, and provided that this is a picture, right? I have the laser beam coming here, the objective is here, and my sample is here, and there is some illumination coming from LED light here. And then this objective not only produces this focusing, but also allows me to make movies, right? And it produces an image, an optical image of the particle that I'm going to trap. Remember that the particle is trapped at the focus, so I have sharp images of the trapped particle. So that works provided that it's highly focused, and provided that there is no much reflection, right? Because reflection of this in this simple ray optics picture leads to radiation pressure that is going to push instead of trap so I need a lot of refraction and the least amount of reflection. So refracted rays will pull the particle towards the focus, but reflected rays will just push the particle away. So that means that this particle has to have very small reflection coefficients, if I think in terms of ray optics, dielectric constant higher than the environment, but not much, slightly higher. This is precisely the condition that I need to have a situation where the positive Matsubara frequencies are small, right? So in other words, situations such that the zero frequency contribution is relatively big or bigger than the positive ones are precisely the situations where it's possible to trap the material. So for instance, silica. Another example is polystyrene, both in water, okay? So the relative refractive index is slightly larger than 1, but not much. So we are going to do the experiment with silica, right? Silica particles in water. So in this example, this thermal limit is already there at distances of 100 nanometers, precisely for the same reason why I can trap the particle, right? Because the reflection coefficients are small. Another very nice feature of tweezers, optical tweezers, is that the trap stiffness is proportional to the laser power, so I can tune the trap stiffness depending on the magnitude of the force I want to measure. So if I want to measure very weak forces, it's a good idea to have very soft trap with a stiffness of this order, femtonewton per nanometer, which means that if I am able to measure displacements in the nanometer range, I will be able to measure femtonewton forces. This is what we have done. So there are many previous experiments, important ones with the interaction across an electrolyte, across a polar liquid, water, ethanol. Jeremy has made experiments with ethanol, right? When we take a metallic surfaces at distances, say, of 100 nanometers or so, because they are metals, right? The zero frequency contribution is not that big any longer, right? So it's difficult to understand how the screening affects the result, because it's affecting just a very tiny fraction of the total signal, right? On the other hand, measurements with dielectric surfaces, so smaller reflection coefficients, they are usually done at a much shorter distance, a few nanometers, because with dielectric surfaces, the signal is going to be weaker. So people usually go to shorter distances, right, in order to be able to measure. And in this case, again, the zero frequency contribution is going to be very small, because now the distance is so small that I'm close to the zero temperature case, more or less, right? So it's also not so what we want to do is to combine these two things, right? Measure the 100 nanometers with dielectric surfaces. Of course, what happens is that the signal is going to be very, very weak, right? But optical tweezers can measure very weak signals. So this is the idea of the experiment. So I have my silica bead, which is optically trapped by the laser beam here. And then I have another silica bead, larger, which is just sitting on top of the glass on the bottom of my sample. So when I approach by just moving using a piezo and moving the microscope stage, I'm going to have this interaction. For instance, suppose the interaction is attractive, then I will displace my sphere laterally, and since I know the optical stiffness of my trap, I can measure the force by measuring the displacement. It turns out that it's better to measure not only the average, the equilibrium position, but the fluctuations, right? The Brownian fluctuations are going to give us a lot of information. So, in a very soft trap, my trapped bead is going to fluctuate a lot, right? And these fluctuations will give me a lot of information about the interaction, right? So this is a typical frame that we capture in our system, right? So this is the big sphere, this is the small sphere. They are not, as you might think, they are not attached to each other, because we see the Brownian motion, right? But the optical image, we cannot see, right? What is the distance? Because here, the distance is a few hundred nanometers. But this bead here is really fluctuating. And this is another cartoon of the situation. And what we are going to do is to measure this position as a function of time, okay? The position of the bead is represented by this point, the red point here. I don't know if you can see at the center. So let's discuss some experimental results. So this is a typical time series of the position as a function of time. And there are some, and from there I can build my histogram, right, of frequencies, and then have this probability density. And this is for the case where there is no interaction, okay? So this is perfectly Gaussian, which means that the potential, right, that I get from comparing with Boltzmann factor it's quadratic, right? And indeed, this optical potential in this range is really, really quadratic. This we can show theoretically, right? To an excellent approximation. So when there is no interaction, I just have this quadratic potential, the optical potential, right? And I can, for instance, characterize the stiffness, the trap stiffness from this, right? By fitting this by a quadratic function. Now, these are the results, these black points here, but these black points are when the spheres are close together, only that we are not measuring the Brownian fluctuation along X, but instead we measure the Brownian fluctuations along Y. So since we use circularly polarized trapping beam, we expect that the optical Kx and Ky are the same. So these fluctuations along Y, it's a control for us to see that we have zero, right? And indeed, that's what we have. It's very important then to use this configuration and to measure the fluctuations along Y as well, right? And these are these black points here. This is in the interaction run, actually, when the other sphere is closed. And we compare this result with the result by using another method when the sphere is really isolated, and then I just apply Stokes drag force by moving my microscope stage, and this is called Stokes calibration. And you see that I have very good agreement, and also we have a third way of determining this stiffness, which is the theory that we have, so we can compute the optical force from independently characterized parameters, and they all fit together, right? This is really a linear as expected function, and I have three independent ways of determining this stiffness. So the fact that this works, this method based on Brownian fluctuations works, is very important because it tells us that this is in thermal equilibrium, right? So it took us a very, very long time to reach this level, right? Because otherwise we would have additional noise that would make everything wrong, right? So these are the spheres that are going to be interacting, and then this is the result when I have a rather small salt concentration, so the binding length is such that I still have residual electrostatic repulsion. And this is the kind of signal I have. These are the same, the experimental data here are the same, only comparing with different models for the Casimir force, right? With or without. And depending of if I include or not the zero frequency contribution, right? Which according to us, it should be there, but according to other colleagues, perhaps it's not going to be there. We have different results, but it's difficult to say anything about both fits are okay, and the parameters are also according to what we would expect. The parameters are the density charge of the spheres and the binding length. But of course, we would like to have a situation where there is no electrostatic interaction. And the way to do this is just to add salt, right? And then the binding length is going to be very small. So the screening is going to be very effective, and I suppress the electrostatic repulsion. Of course, what is left is a much weaker signal, right? It's harder to measure, but we have managed to measure. This is the this interaction potential here. So you see, with or without, it shows that the zero frequency is almost everything here in this distance range, right? If I don't have the zero frequency contribution, I have this red line here, which is nearly zero here in this scale, right? So I'm really in this thermal limit, right? Or high temperature limit, if you prefer. So the same I'm showing here for the force, right? Without the zero frequency, with the zero frequency is the black, and we have a reasonable agreement with this prediction that we have for the force with this unscreened transverse magnetic contribution at zero frequency. So in conclusion, we have this shown experimentally, in our experiment, it's compatible with this contribution, right, from transverse magnetic polarization at the limit of zero frequency. This contribution is not screened, so it will be there regardless of the value of the device screening length, even if the device screening length is very small. This makes the interaction in a water solution of a much longer range than previously thought. And this, of course, should have implications in different fields. And this zero frequency is already completely dominant at a distance larger than 100 nanometers. So this function that we have for these two spheres doesn't depend on the dielectric properties of these spheres or on the dielectric property of pure water, and that's universal function of just the geometric aspect ratios. So to give us an idea of how strong it is of the order of kBt when the distance divided by the effective radius is 0.1. So this is a figure to have in mind. So, and we have measured this exactly in this kind of condition, right? Because our radius is around 2 microns, right? And we have measured in this distance range from 200 to 500 nanometers, so close to this situation where the interaction energy is of the order of kBt. So with that, I just want to show the people who has actually done the experiment. I am a theoretician, right? So Luis was a doctoral student with us, and Dene was a postdoc at the time. You know this guy here, right? Ricardo was very important. He stayed a few months with us. It was very important. Nathan is my colleague. He is a true experimentalist. And there are other people and theoreticians. Benjamin is here. He was very important to do the numerical calculations. And so with that, I thank you for your attention.
Thanks for the very nice talk.
Thank you so much. Very nice talk. So I appreciate the results that you presented in the case of screened electrostatics and then also in thermal equilibrium. But there's been a lot of interesting results in the last few years in the case of a driven system that is electrodynamically resonant. So imagine you have two dipoles that are interacting electrodynamically. This interaction is not screened beyond 250 megahertz. This has been known for hundreds of years, right? So what I'm curious about is what you said about the zero frequency Matsubara. In the case of electrodynamic interactions, which have been shown now experimentally in aqueous environments to exist on the micron scale, how do you connect that to the results you're showing for zero and positive Matsubara frequency? Is there a way to think about it?
Yeah, I think precisely what you said is that there is no screening if I do electrodynamic measurement, because the plasma the characteristic response time of the ions is very slow. The ions are too slow to screen if I have something which is orders of magnitude larger than omega p. And omega p for ions, it's in a solution, even if the salt concentration is the highest possible value, close to saturation, it's going to be very, very small. So it's not surprising that all these electrodynamical experiments are not suppressed by screening, right? But what happens here is that in our calculation, also the positive Matsubara frequencies when we compute, they are not affected. It's easy to see that it's completely negligible, the effect of the ions for the, let me come back here just a minute. When I have the sum over all Matsubara frequencies, for all non-zero frequencies, it's also completely negligible, right? I can forget about the ions precisely because omega p is so small, right? Precisely because omega p is so much smaller than kBt over h bar in our case. What about the zero frequency then? And at the zero frequency, of course, it's something different, right? I mean, I have the impression that sometimes, not in the Casimir community, but in this colloid community. You tend to treat the zero frequency as something that has to be considered apart, right, from the rest. But here in the Casimir community, I think most of you agree that the zero frequency is just another pole, right, of the hyperbolic cotangent, right? It comes, has to be treated on the same foot, right? By the same formalism, and I take the zero frequency limit only at the very end. This is what we do in Casimir usually, and this is what we have done here too.
And what do you think is a measurement possible in a driven case or in an out of equilibrium case? Can you make a Casimir measurement in that context? If you were to, in other sense, your two interacting spheres are resonant, and you've driven them.
But by oscillating spheres,
essentially you create an antenna, two antennas that it could interact.
This is, I think it's possible, yeah. I mean, the problem here is always that we are already at the limit of our sensitivity, right? So that doesn't make much room for more complicated experiments. But of course, if you are able to optimize things a little bit, we could think of more challenging experiments.
Thank you.
I have the same question actually related, which is that can you observe the tweezer-induced modifications to the force, and because that's going to scatter photons, and then is that already included, or is that something you can observe separately from the vacuum part?
Okay, there is I think what you are mentioning perhaps is that when I approach one. When they get close to each other, does the presence of the other sphere changes the optical force, right? For instance, this is what you mean, right?
So what I mean is, right, so there will be a contribution where, let's say, the tweezer photons are being scattered into the vacuum modes, and then that leads to a contribution that depends both on the tweezer intensity as well as the distance
I see.
L.
Yeah. We could try to look for this kind of, because what you're saying is that we have these two separate things here, right? I mean, the optical force, which is completely classical, because this laser beam, it's really, well, there are many photons there, even if we are using low power. And the other, and there are these electromagnetic modes here, right, that make this reverberation between the spheres. And can I treat these two things separately or not? We have done this separately, right? But to what extent this is accurate?
Right, there will be some cross-talk between the two. So yeah, I guess that
would
would be interesting.
Could be, but
discuss.
I mean, at the level of our experiment, the precision is really very, very small compared to the. So again, it's like the previous question. I think we would need to really optimize many things in order to see non-trivial effects like this one we were mentioning.
Thanks.
Thank you for the nice talk and for going through everything so carefully. This was very helpful. I have a basic question. I'm not able to understand in your dielectric constant expression that you had the longitudinal one, which had the Debye kind of frequency, the Debye screening, as well as the transverse one, for which you only had a local. Right. So the reason, maybe I can explain why I have the question. So in solid state, as you know, for k equal to 0, the longitudinal and transverse dielectric constants are the same. And for k non-zero, the longitudinal and transverse are different, but they have the same k dependence in crystalline lattices. So I'm trying to understand why in this case, the transverse one was local, but the longitudinal one was non-local. Yeah.
Yeah, yes, clearly, yes. This is local, no k dependence, right? And this is contains this k dependence. And I even don't know if I take k equal to 0, I think they are going to be the same, right? Yes, at least that is satisfied. But the other part, it's not, right? I don't have an argument for this, why this, I have some colleagues in France that have some arguments why there is no K dependence for the transverse modes in this context, right, of electrolytes. But it's more like a calculation. It's not really a hand wave argument. So this
maybe
this
a comment on that.
From sorry,
a comment on that is in terms of elasticity.
Mm-hmm.
I think you can understand it. This longitudinal one is related to compression.
Right.
The liquid has
Uh-huh.
there's a restoring force against compression, and the other one would be shear. So there's no shear elasticity if it's a liquid. Mm-hmm. That's why the transverse one.
That's the difference between the liquid and the crystal, right? Yeah. Thanks. Yeah. Good point. Yeah.
Any other questions?
The salt that you used in the experiment, it was just monovalent salt.
Yes, it was iodate of sodium iodate. Right?
So
that was a tip that was in the that was the. I think we took from your paper actually because you were using this salt as well, so we decided to use it. But I don't know if it's the best optimal choice. I would like to hear from you about that.
Yes, because in the colloid community, you can get some weird effects if you have non-monovalent salts.
Because but it's monovalent, right? But this iodine, it's a very big ion, right? So there are some special effects that I learned after, right? That because of this characteristics of iodine, it could be some interesting effects could appear. So in the end, it's not sure that it was the best choice, but it was okay. I think for the distances we have probed, and it's the same for Jeremy's experiment, I don't think this ion specific effects would play any role at distances of 100 nanometers and beyond. It's the same case of Jeremy's. But if you were going to probe at shorter distances one day, I don't know if you can do it.
Because when you have these systems, you can actually go into a strong coupling regime. You have to be a bit careful because the form of the dielectric constant there is effectively what you get from Debye-Huckel theory, right? So it's, I mean, in principle, the electrolyte isn't a Gaussian field theory. It's a full interacting field theory and the corrections to those terms, right? So, and those corrections become more important when you don't have monovalent salts.
Okay. So it's nice to plan future experiments, right?
Yeah, I mean, it'd be interesting to play around with.
Or on the other hand, it would be interesting to probe such effects as well, right?
Yeah. Okay, thanks very much.
Thank you, David.
Other questions?
So just a comment, for these aqueous media, this is fine in kind of Lifshitz theory, but as you go to these nanometric scales and beyond, right? If you take a sort of many-body van der Waals approach to treating the aqueous media, you're going to see changes to the dielectric, right? And these actually have long-range implications. So it's something we've done. Maybe we can talk about. It's something that, in terms of understanding how this screening matches with theory, you might want to consider.
Okay. Thank you.
Any other questions or comments? If not, let's thank the speaker again.